Okay, let's do some stoichiometry problems. The first question states that nitrogen gas can be prepared by passing gaseous ammonia over solid copper oxide. So nitrogen gas is a diatomic molecule. That means each molecule of nitrogen gas has two nitrogens, N2, and that's just something that we got to memorize. Gaseous ammonia is NH3, and that's also something you must memorize. You'll see that appear in problems occasionally, and just know that whenever it says ammonia, it's NH3. Keep in mind that's different from ammonium, which is NH4 plus. Okay, and it says that nitrogen gas is being prepared, so we know it goes on the product side. Gaseous ammonia over solid copper oxide. So from our transition metal naming, we know this is CuO because copper has a -2 charge. This is solid. The other products of the reaction are solid copper, so copper solid, and water vapor. Water vapor is just water, but it's in a gaseous state. Okay, so when you boil water, the steamy stuff that comes out is water vapor. Now, this is a stoichiometry problem because it asks for the limiting reagent and asks how much N2 will be formed. When we're dealing with a stoichiometry question, we always need to balance the equation first. That's the first step, balance. Okay, so how do we balance it? Well, we see that, well, on the right side we have two nitrogens, on the left side we only have one, so I'll put a 2 here, my bad, a 2, once a 2 here, and that gives us 6 hydrogens. So on the right side we gotta have 6 hydrogens, so we put a 3 here. 3 times 2 is 6. That gives us 3 oxygens though, so on the left side the only compound with oxygen is copper oxide, so we gotta put 3 over here to balance the oxygens. And finally we got 3 coppers on the left side, so we gotta add 3 coppers on the right side. So this is a balanced chemical equation. The second step is to convert to moles. Okay, anytime you're dealing with a stoichiometry question, you always have to convert to moles. That's always. So we have 18.1 grams of ammonia and 90.4 grams of copper oxide. Okay, so we got to convert both of these to moles. Why do we need to do that? Well, first off, we need to figure out the limiting reactant, and after that, after we found the limiting reactant, we want to figure out how many grams of nitrogen will be formed. And to figure out how many grams, we have to figure out how many moles first. And how do we figure out how many moles? We use a mole ratio from the either ammonia or copper oxide, the mole ratio of, let's say, for example, ammonia to nitrogen gas, and from there we can figure out how much. Once we find the moles of ammonia of nitrogen gas, we can figure out how many grams of nitrogen can be formed. Okay, so let's figure out how many moles of ammonia gas. Well, that's just moles is equal to mass over molar mass. Okay, so mass is 18.1, molar mass is 14 because that's 1 nitrogen and we have 3 hydrogens, so it's 1.0 times 3. Okay, so let's do that. 18.1 over 14 plus 3.03. That gives us 1.06. So 1.06 moles. Okay, so we have 1.06 moles of ammonia. Let's do copper oxide, same thing. 90.4, the molar mass of copper oxide is, actually we can just do it here. Okay, molar mass of copper oxide. It's 1 copper atom, so that's 63.55 plus oxygen, which is 16.00. And when we add that, we get 63.55 plus 16. We get 79.55 grams per mole because it's a molar mass. Okay, so we have 79.55 grams per mole, and divide that by 90.4. Actually, let me just write that down. Actually, 90 divided by 79.55. Oh, my bad. This should be moles now. So moles is equal to 90.4 grams divided by 79.55, and we get 90.4 over. We get 1.136, 1.14 moles. Okay. Now we have to ask ourselves which one's the limiting reagent. we would have to do a mole ratio now, because even though copper oxide has more moles, you need more copper oxide per ammonia, right? For every 2 ammonia, you need 3 copper oxide. So copper oxide should have more moles. I'm going to just record ammonia has 1.06 moles and copper oxide has 1.14 moles, okay? So let's do the mole ratio. Okay. So ammonia to copper oxide is equal to 2/3. And let's just choose one. Let's just say ammonia. If we had 1.06 moles of ammonia, how many moles of copper oxide should we have? So this would be our x. And when we solve for that, we get 1.06 divided by 2 times 3. We get 1.59. So if we had 1.06 moles of ammonia, we would need 1.59 moles of copper oxide, but we don't have 1.59 moles of copper oxide. Copper oxide is equal to 1.59. We don't have 1.59 moles of copper oxide. We only have 1.14. So copper oxide is a limiting reagent. We don't have enough of that. Because we have 1.06 moles of ammonia, we need to match that with 1.59 moles of copper oxide to make the mole ratio 2:3. But we don't have that. We only have 1.14 moles. So copper oxide doesn't have enough. So that's the limiting. And the excess is ammonia. So this is the limiting. Now, after that, once we find the limiting, we forget about the other value. We forget about how many moles of ammonia, because it doesn't matter if we have 1.06 moles, 2 moles, or 3 moles. It's going to be in excess. There's going to be left over. What's really going to determine how much we can make is the copper oxide. So we do a mole ratio with copper oxide now. We're going to figure out how many moles of nitrogen gas. So nitrogen gas over copper oxide is equal to 1/3. The mole ratio, there's a 1 here, 3. And how much copper oxide do we have? Well, we have 1.14. So this will be x, because when we figure out how many moles of nitrogen we have, nitrogen gas, when we do the mole ratio, when we solve for x, we get 1.14 divided by 3. X equals 0.38. X equals 0.38. Okay, and that's moles. So x equals 0.38 moles. From moles, we can figure out grams. I'm going to erase everything now and just figure out the grams of N2. So we know the moles of N2. Moles of N2 is equal to 0.38 moles. And we know, and using the formula, moles is equal to mass over molar mass. We can figure out mass, and that's what we want. We want grams. Gram is the key word for mass. Mass is equal to N times molar mass. So we have 0.38 moles. And we multiply that the molar mass of hydrogen, which is 14.01. And we get a value of, 0.38 times 14.01. Get a value of 5.3. Okay, so we get a value of 5.3 grams. Okay, so to answer this question, what is the limiting reactant? Copper oxide is the limiting reactant, and we will produce 5.3 grams. Okay, if we had more copper oxide, we would produce more nitrogen gas. If we had more ammonia, we would still produce the same amount of copper oxide, because after this reaction is over, we still have some NH3 NH3 compounds floating around. They're still left over. We have them in excess. That's why it's called the excess reagent. Okay, next question. The reaction between potassium chlorate and red phosphorus takes place when you strike a match on a matchbox. If you were to react 52.9 grams of potassium chlorate with excess red phosphorus with mass of tetraphosphorus dicoxide, would you produce? Okay, so it says that it's unbalanced, so we need to balance this. Let's see how we can go about this. We have 10 oxygens here. 1, 2, 3. Okay, that's a bit tricky. Well, that's what we can do. Lowest common denominator between 3 and 10, that would be 30. right? So we do 3 here and 10 over here. If we have 10 potassiums, we need to put 10 potassiums here. That balances the chlorides. And if we have 3 times 4 phosphorus, we need 3 times 4 phosphorus on this side, and this becomes balanced. Because if we count the oxygens 30, potassium 10, chloride 10, and phosphorus 12. And on this side, when we count oxygens, we also get 10. Oh, no, we get 30, my bad. 3 times 10, this is 10 times 3. Potassium, that's 10, chloride, that's 10, because of this compound. And phosphorus, we also get 12. 3 times 4, that's 12, okay? So 10, 3, 10, 3, 3, 10. It's balanced. And it tells us that we react 52.9 grams of potassium chlorate with excess red phosphorus. So when we know it's excess, that means we have so much of this that this is going to be the limiting reactant. Think of it like that. So our first step was balance, which is what we did. The second was convert to moles. Okay, so let's convert to moles. 52.9, convert it to moles. What's the molar mass of potassium chlorate? Let's figure it out. Molar mass of potassium chlorate. Okay, so molar mass of potassium chlorate. Okay, potassium is how much? Potassium is 39.1. 39.1. Chlorine, this chlorine over here is 35.45. 35.45. And the 3 oxygens is 6 oxygen. 1 oxygen is 16, so we have 3 of them. 16 times 3. Okay, so it's 39.1 plus 35.45 plus 16 times 3. When we do that calculation, we get, let's do 39.1 plus 35.45 plus 16 times 3. We get 122.55. So if we had 6.02 times 10 to the 23 molecules of potassium chlorate, it would weigh 122.55 grams. Okay, 122.55 grams. 122.55 grams. Okay. And we know moles is equal to mass over molar mass. So we have the mass of 52.9, well, actually right on the same line, 52.9 grams divided by the molar mass, which is 122.55. 122.55. This is a 9 and this is grams. Okay, grams per mole. The grams cancel and the mole moves to the top. And you get 52.9 divided by 122.55. 0.432 moles. Okay, so we have 0.432 moles, and I guess the third step you could say is mole ratios, right? What do we want to figure out? At the end of the day, we want to figure out tetraphosphorus dicoxide. Okay, it asks for mass, but really, in order to find mass, you need to find moles, and that is all the time. Anytime they ask for mass, just know that you have to find moles first, always. That's always. Anytime they ask you for anything of a compound, always find moles first, and if they're asking for mass, just convert that moles to mass, okay? So mole ratios, 0.432 moles. Tetraphosphorus dicoxide, so 10 oxygens dicoxide, P4O10. So the mole ratio of P4O10 to what moles do we have? We have moles of potassium chlorate. So of chlorate is equal to 3, because the coefficient here is 3, divided by 10. Okay? And what do we know? We know potassium chlorate. We know it's 0.432. 0.432. And we don't know P4O10. So we put X here. X is equal to, and solve for X. We get 3 over 10 multiplied by 0.432. We get 0.130. Keep in mind these have infinite significant digits, because all this is saying is that for every three phosphorus molecules, you need 10 potassium chlorate molecules. So it's it's like counting for every 10 marbles you need 3. For every 10 blue marbles you need 3 red marbles. It's an exact number. So these have infinite significant digits. Okay, so 0.130. That's how many moles of tetraphosphorus dicoxide. C4O10, 0.130. And from there, we can figure out the mass of tetraphosphorus dicoxide using once again the mole formula, I guess. Moles is equal to mass over molar mass. So I don't know if there's a name for this, but I call it that, the mole formula. And we can solve for mass by multiplying by molar mass. Mass is equal to moles, which is n times molar mass. And that is equal to, well, we know the moles of our tetraphosphorus dicoxide is 0.130, and we multiply that by the molar mass. Well, we got to figure out the molar mass of tetraphosphorus dicoxide. So let's go back. And okay. So I'm going to erase this. Molar mass is equal to, okay. So tetraphosphorus dicoxide. This is phosphorus, but since it's tetra, we have 4. So 30.9, 30.97, but we have 4 of them, so we multiply that by 4, not 3. Since tetraphosphorus dicoxide, deca is 10, so we got 16.00 times 10 of these, okay? So it's 30.97 times 4 plus 16 times 10. That's the molar mass of tetraphosphorus dicoxide. And all that's saying is, in one molecule of tetraphosphorus dicoxide, it's going to weigh how much? And that's going to be the value we get when we do this calculation. So 30.97 times 4 plus 16 times 10. Okay? 16 times 10. We get a value of 283.88. 283.88. So that's grams per mole. 283.88, 283.88, and you can do the units here if you'd like. This is moles. Yeah. There's grams per mole. These moles cancel, and you're left with just grams, which is mass, which is what we're looking for. Times 0.13, we get 36.9. 36.90 grams. Okay, so that is the mass of tetraphosphorus dicoxide that we produced. Notice here that in our balanced equation we had 10 over here, 3 over here. So even though we had more potassium chlorate when we started off, we produced less tetraphosphorus dicoxide, even though the molar ratio is different, because tetraphosphorus dicoxide weighs a lot more than potassium chlorate. You know, one molecule of the molar mass of tetraphosphorus dicoxide is a lot more than the molar mass of potassium chlorate. And that's because the mass of one molecule of tetraphosphorus dicoxide is a lot more than potassium chlorate. So those are the two examples for stoichiometry.